Hello, my name is Neeti Swami,
And my name is Dzmitry Savitski.
and today we are presenting about the synthesis and characterization of copper-1 asymmetric phenanthrene N-heterocyclic and 1,3,5-7 compounds, specifically for use as antimicrobial agents, but we'll also be looking at their general properties as well. We are doing this research as a part of Dr. Calcidante's lab, and we will be starting off our presentation with a brief overview of what we do. So we are synthesizing copper compounds in a variety of ligand environments. These ligands include 1,7-phenanthrene, 4,7-phenanthrene, 1,10-phenanthrene, BPY, TPY, and what we're doing is comparing how these ligands bonded with copper compared to similar ligands bonded with silver and gold. So for example, phenanthrolenes, when bonded with silver and gold, have been shown to have antimicrobial properties. And so we're trying to create analogous compounds, except with phenanthrolenes and copper, to see if we can have comparable antimicrobial properties while using a much less expensive, much more accessible metal like copper. Another very important ligand that we're using is 1,3,5-7-phosphatamantane, or PTA. PTA is a water-soluble compound, and so when it's bonded into other compounds, it can potentially make them more water-soluble. So let's say, for example, we have a copper compound that is bonded with phenanthrolenes and then also with PTA. We have a much less expensive compound. It's antimicrobial, and then it's also water soluble. So that means that it can be delivered in the bloodstream as a medicine. It can be used in more aqueous solutions, like if we want to spray it on a surface. And so there's a lot of applications for it. So now that we've talked a little bit about what we're trying to achieve, let's talk about how we actually synthesize these compounds. So two of the major instruments that we use are one, a round bottom flask, and then two, a vacuum filtration setup. So the round bottom flask, we put our reagents into the round bottom flask. There's a magnetic stirrer, and we let it react for as long as needed, depending on what ligands we're using. We change out the solvent so that depending on whatever reagents we have, they're soluble in that solution. On the right, the way we use the vacuum filtration setup depends on what reaction we're on and what we're trying to obtain. So let's say, for example, we're on a final step of a reaction where we're adding in the PTA or the phosphatamantane. Well, instead of, when we're looking for our product, it's not going to be on top of the filter. It's going to be in the flow through, in the solution that's aqueous, because if we have PTA in our compound, we're hoping that it would be water soluble, and so it should be in that solution rather than on top. But let's say we're on an intermediate step in our reactions, then most likely our compound is still insoluble, and so we would find it on top on the filter rather than in our solution. So Dzmitry is going to be going a little bit more in depth into the actual reactions that we're doing.
At the top of this slide, we've put many of the different reactions that we've carried out so far, as well as the products that we hope that we synthesized through these reactions. And then at the bottom here, we have a variety of different ligands that we used in the reactions above. And then I just wanted to point out that the structure of the PTA, this is the picture on the bottom left. And then the phosphorus atom in the structure bonds to the copper whenever we synthesize the PTA containing copper compounds. For many of these reactions, we use tetrakis copper-1 hexafluorophosphate as the base, as like the starting material. And the reason why we use this compound is because it has a number of acetonitrile groups, and these groups can be easily kicked off in future reactions to add other compounds to it, such as the phenanthrolenes or PTA. And so this allows us to easily add these compounds and get our desirable products. On this next slide here, we have a variety of different compounds that we've synthesized so far. And as you can see, they come in all sorts of colors. And then as you can see in the image in the top right, this image was taken when they were exposed to long wavelength ultraviolet light. And as you can see, many of them have fluorescent properties. And then down below here, we have the chart of these that has all these different compounds, as well as the properties of these compounds, such as the color and luminescence, and then also the solubility. We've found that attaching PTA to these compounds does increase the solubility of these compounds in water, but it only does so to a certain extent, so many of them are still only slightly soluble in water. One of the major problems that we've had so far while synthesizing all these products is that we're not sure if our reactions were carried out successfully, so we don't know if the product that we wanted to obtain is actually the product that we obtain, or if there have been other side reactions that produced other undesirable products. And so we've noticed this in some of the experiments that we've done, such as TLC, so thin layer chromatography. We would try to separate the products based on their polarity. And we've noticed that many of the products have more than one product within them. So it would separate into different bands on the TLC, indicating that there are impurities. And so we're going to do a variety of other experiments, such as we've already been doing a lot of crystallization, and we have had limited success, but we're going to continue trying. And then, like with crystallization, we try to grow pure crystals of the compound so that we can clearly see the structure of these products that we're making. Then in addition to this, we're also doing NMR. We're doing both hydrogen NMR, and then we're also going to do phosphorus NMR. Because as I mentioned previously, PTA has phosphorus atoms in its structure. So we'll be able to look at those compounds that have PTA in them using PNMR, phosphorus NMR. And then lastly, we'll also be doing a lot of UV-Vis, and these experiments that I mentioned are all for the purpose of characterizing the products that we made and making sure that we're actually successfully carrying out these reactions. And then next up, Neeti is going to talk about some of the microbial work that we've done so far.
So like Dzmitry said, we are still in the process of analyzing our compounds and detecting their purity. And so right now, we haven't actually been using our synthesized compounds for our antimicrobial testing. What we've more so been working on is refining the protocol and replicating the antimicrobial testing protocol that we've seen in literature. So we've been using the Kirby-Bauer test, which is normally used to test sensitivity of bacteria to various compounds. Right now, we're trying to standardize the protocol and find a working positive control. So right now, the positive control that's in this picture is kanamycin. Kanamycin is known to work against E. coli. E. coli is the bacteria that we're using currently in this picture. And it lets us know that it gives us a source of comparison against a antimicrobial disc that we know works well. So we know that kanamycin works well against E. coli. And so when we apply our own compound, we'll be able to see how it compares to a very well-working antibiotic like kanamycin. Some of the challenges that we've had with replicating this protocol is, one, we don't want kanamycin to be our positive control. We want a phenanthrene, for example, that we know is supposed to be antimicrobial by itself to work as our control. And so there's been a lot of variables that we need to consider when we are doing this protocol. So like one, for example, what solution is the phenanthrene supposed to be soluble in by itself versus when it's in our synthesized compound? Is phenanthrene effective against E. coli? E. coli is a gram-negative bacteria, or is it supposed to be more effective against gram-positive bacteria? Over in this picture on the left 5 plates are a 2 McFarland standard versus the 5 plates on the right are a 1 McFarland standard. So the McFarland standard is supposed to be used to detect the density of growth of bacteria, and it's used to standardize the level of bacteria growth on the plates. So that way we can measure the zone of inhibitions, or that dead space around working antibiotic discs, so that we can see how effective it is. But detecting what level of McFarland we want to be at and what McFarland that literature says that we're supposed to be at has been a challenge. So there's a lot of different things to consider when we're doing this protocol. In the plates that we have in the picture, there are 5 different sections. And so when we are testing the plates, we have multiple things that we're considering and testing to use as sources of comparison. So like I said, we have a positive control that ideally would be one of our ligands that we're using in our synthesized compound. In our example, or in the picture, it's kenamycin. We also have a negative control like water. Water isn't supposed to do anything. It just lets us know that things aren't being killed accidentally. We have a low concentration of our compound, a high concentration range of our compound, so that we can see a range of how effective our compound might be at different concentrations. This is also ampicillin resistant E. coli. So we have an ampicillin disc in one of the sections. So that way we know if the ampicillin has killed bacteria, we know that the bacteria that we grew was most likely contaminated. So there's a couple plates where there's the ampicillin disc and the bacteria around it is dead. We know that there was a contaminant inside, but in most of the cases, the ampicillin disc has been grown over by bacteria, so we know our bacterial growth was good. So this has just been an ongoing process as we are also working to purify and analyze the compounds that we've synthesized. So like I said, like Dzmitry said, we have various things that we need to further investigate, including the exact structure of their compounds, farther look into their luminescence, and eventually their antibiotic properties. In addition, we've also been able to see, though, that PTA does add water solubility to the compounds that they're in, but we're not sure the degree of that water solubility, and we've seen that it's highly versatile between compounds, very highly variable. We've also seen that ligated copper compounds are able to fluoresce under different kinds of wavelength, and we'd like to further investigate how that might affect the compound. And now we have come to the end of our presentation. We would like to thank Dr. Casadante and the graduate students in our own lab for all of the hard work that they've done to support us. We would also like to thank Dr. Kyle's lab, who has been assisting us in the antimicrobial testing process. We'd like to especially thank Chaitanya Haram, who's a graduate student who's been working closely with us there. And additionally, we would like to thank the Honors College Undergraduate Research Scholars Program that is supported by the CH and Helen Jones Foundation, as well as the Pi 2 program, which has helped make this presentation possible. Thank you very much for listening, and we appreciate your time.